I think in 9, they actually instead tell you the quadrant. So in quadrant 4. Now, being told that the sine is negative and the cosine is positive, you'd have to be in quadrant 4 anyway. So either way, that information is given. It tells us the same thing. It tells us that our angle is down here. Now, your number 9 might have different numbers other than 12/13. And actually, one of the things about number 9, is that it's not nice numbers like 12/13. 12/13 might not seem nice, but in terms of right triangles, it is. Because that's part of the 5, 12, 13 Pythagorean triple right triangle. So let's go with the 2/5. That's what my number 9 up here has. So if the cosine is equal to 2/5, that tells us what the ratio between the x value and the radial value is, or in terms of our triangles, the ratio between the adjacent and hypotenuse. Now, we could put this on the unit circle and say that's 2/5 on that side, and that's a 1 on that side, if we wanted to. But generally, we don't. Generally, we say, okay, this side is 2 to that being 5. But both are correct. As long as they're in that ratio of 2 to 5, it's fine. You could put 4 and 10 if you wanted to. Is that part fair?
Yes.
Okay. Okay. So if we're going to answer what the sine, cosine, or we know the cosine, the sine, tangent, cosecant, secant, cotangent, if we're going to find what they are, we've got to find this other side length. And I really do recommend drawing these diagrams every time you have these, because we're going to actually be doing more and more dramatic things with this as we go along. So getting used to drawing the diagram so you can see what you're doing is really helpful. Now, the relationship that we know between those sides is that Pythagorean theorem should hold. So 2 squared plus b squared has to equal 5 squared. So 4 plus b squared is 25. So b squared is 21. So b is plus or minus the square root of 21. Now, I've talked about stressing that we have to remember that plus or minus, and this is one of the reasons, one of the many reasons why we need to decide whether we're going to use the positive or the negative there. And because we're in quadrant 4, what do we know about our y value?
It's negative.
It's negative. So we have to specifically use that negative square root of 20. And this is why I say when I say to draw these diagrams, don't just draw a triangle and say, oh, that's a 2 and that's a 5, because that'll end up being a positive because you're just thinking about a triangle and you're not going to end up with the right positives and negatives. So make sure you're whether it's given to you as the sign is positive or negative, or given to you as a quadrant, make sure you take that into account in your diagrams as well as your work. But as soon as we know that, we know the excuse me, the sine, the tangent, and anything else that we want. We know the sine would be the y value over the r value. Tangent, the y value, or if you prefer, the opposite over the adjacent. Cosecant is the reciprocal, so you'd be sure to rationalize it, and so on. So does that, I went through that a little bit fast, but does that help? Is that, what part of that was getting you stuck? Was it the negative? Was it the square root?
Yeah, this definitely helps. I had a question. What about if the cosine instead of 2/5 would be like negative 2/5?
Well, if it had been negative 2/5, then it couldn't have told us we were in quadrant 4 because cosine can't be negative in quadrant 4. Fair?
Yeah.
So that already would have been like, that can't happen. But if it had said the cosine was negative 2/5 and the sine had been still negative, well, that combination, a negative cosine and a negative sine, would tell us we have to be in quadrant 3. So we'd have been down here. Fair? That would have made our x value the -2, our hypotenuse the +5, because again, that radial length, that r, is always positive. Pythagorean theorem would have given us the same result, and being in quadrant 3, we'd have still had that negative square root of 21. So our sine would have been the same. Our tangent, they both would have been negative. So we'd have ended up with a positive square root of 21 over 2. Cosecant would have still been negative. So it wouldn't have changed all of them, but it would change the sign of some of them. It would have changed the sign of anything that involves that -2 value. Does that work?
Yes, thank you.
Sure. All right. Let's see. So most of you played with a lot of 6-5 or 6-4. That's good. A couple of you started playing with 6-5. Hopefully you guys looked over 6-5. I did say I wanted you guys to make sure you read it before we talked today. Okay.
One last question.
Yeah.
Is it really important for us to memorize the unit circle going forward, especially concerning, like, say, tests and stuff?
That's actually a surprisingly complicated question. First off, I generally tell people, do not memorize the unit circle. Now, when I say that, it's because I'm about to tell them, instead of memorizing that, learn to build it. And they go, oh, well, that's the same thing. I don't think it's the same thing, but I think I suppose we could debate that if you wanted to. So I have been encouraging you guys to learn to do the construction and the counting. Have you guys practiced that? I got one yes. Victoria's still smiling. Victoria, you're always smiling. But I never know what it means. So I do want you guys to be practicing this construction. Because if you do, it'll help a lot with knowing these values and being able to pick them out when you need them. That being said, it can take, 10 or 15 minutes to write it all out. So for something like a test, I don't expect you guys to kind of just have this floating around in your head, and having to write it out every time on a test would take an extra, some extra time that you don't need to spend. So you will have a copy of it on the test, on all the tests that you're allowed to use. That being said, I don't want you to take that as I don't need to practice, like where it comes from and how it's built and all that. So is that a reasonable answer, Corey?
Well, again, in the context of my question was actually the 6-6, or the only way to know what to do by hand is to give you a sign, say, okay, here's the angle, is you would have to know what all the science and stuff for the standard angles are.
Right, but if you know what quadrants you're in, you automatically know whether they're positive or negative, and it's only two triangles that we have to know. So if we know those two triangles, you can build those answers fairly quickly. But on a test, after only a few weeks, yes, you'll have a circle because it can be hard to do all at once. But ideally, you'll be getting familiar enough with the circle that you'll be using the copy of the unit circle that you have to check your logic, as opposed to, well, I have no idea, and I know this tool is supposed to tell me, but I'm not sure how. Fair? So you want to get
Okay,
comfortable.
actually, that makes sense. If I just make the quadrant and do just those sines, cosines of that quadrant, then that wouldn't take terribly long, but we wouldn't take, and I'd be able to come up with the corresponding angle.
But all that being said, you will have a copy of it.
So are we going to be like in a Zoom class while we're taking the test?
Nope, but you will have a reference sheet that will come with your tests that you're allowed to use during it, and you shouldn't be using any other outside resources.
Okay.
Excuse me. Okay. One thing about this unit circle is that while it is a great tool for finding values and us learning what the geometric functions do, it's important to recognize that this circle is the graph of, well, a circle. The equation of that circle is x squared plus y squared equals 1. Radius 1 circle. It is not the graph of the sine function or the cosine function or the tangent function. If we want to look at a graph of y equals the sine of x, you could use any variable you want there. We're just used to graphing things on an xy coordinate system, excuse me. So when we talk about x and y's here, this x is our input for our sine function. So this x is our angles. So instead of looking at our angles as kind of visually occurring, our angles are now listed out along that x-axis. So if we were going to put it in degrees, and wanted to do one rotation, we'd put like 360 degrees there, 180 degrees, 90 degrees, 270 degrees, negative 90 degrees, and so on. You know, we could do 45 degrees, 135 degrees, and so on. Fair? So instead of actually visually having a visual of these are our actual angles geometrically, we are listing them out and looking at what their values are and how their values change over time. And one of the things this moves us to is, instead of just being able to make arguments geometrically, we can now think of those angles as occurring over time. So this starts us, kind of begins our conversation about thinking about trig functions in terms of, instead of just geometric angles, in terms of an oscillation over time for things like tides and blood pressure and all kinds of good stuff. A couple of references here. If this is, say, 90 degrees, that means the angles that occur between here and here, between 0 and 90 degrees, this is a representation of quadrant 1. Quadrant 1 is occurring in that column. And then the angles between 90 and 180, quadrant 2, those quadrant 2 angles are going to be mapped into that part of our x-axis. You might say, well, this isn't quadrant 2. Quadrant 2 is over here. Yes, but this is where our quadrant 2 angles are being mapped to. Does that distinction make sense? So be careful about that. And similarly, quadrant 3 and quadrant 4. But then if we keep going, after quadrant 4, we're going to get quadrant 1 again there, right? We're going to get things between 360 and what, 450, things in that are coterminal to those quadrant 1 angles. So we're back into quadrant 1, and then quadrant 2 again, and quadrant 3 again, and so on and so forth. If we go back the other way, between 0 and -90, this is our quadrant 4 back here. And in front of that, quadrant 3 and 2 and 1 and so forth. That seem reasonable so far? All right. Now, if we're going to graph our sine function, let's look at what that sine function does. That sine function is supposed to be the y values on our circle. So if we start at an angle in standard position of 0, either degrees or radians, if we look at what happens in quadrant 1, well, it starts with a y value of 0 and then increases to a y value of 1. So it's going to start at 0, goes to 1/2 pretty quickly, and then root 2 over 2 and square root of 3 over 2. Now, square root of 2 over 2 is about 0.7. Square root of 3 over 2 is almost 0.9. So it kind of goes up quickly and then levels off to that 1. And that 1 is the highest y value that's going to occur. Fair? So the sine of any angle is never going to be bigger than 1. It's kind of trapped there. Well, then what happens to the y values? The y values go back down. Square root of 3 over 2, square root of 2 over 2, 1/2, 0. So what do? In quadrant 2, whether it's in degrees or radians, in quadrant 2, it drops down back to 0. Well, then what happens? In quadrant 3, we start getting negative sine values, because sine is negative in quadrant 3. But it's the same values, right? I haven't written them here, but it's the same 1/2 square root of 2 over 2 and square root of 3 over 2, because it's still those same triangles down here that were up here. It's just now they're negative. So it's those same values going from 0 to 1. It's just doing it in the negatives. What about quadrant 4? Well, quadrant 4 is going to start at that -1. And the y values are going to decrease. Negative square root of 3 over 2, negative square root of 2 over 2, negative 1/2, negative 1/2, and then back down to 0. So when we look at or think about our graph of our sine function, this wave is technically referred to as a sinusoidal wave. That waveform is what we should associate with what the graph of our sine function looks like. And if we tried to keep going here, and we certainly should because things keep rotating, time keeps on, if we go back into quadrant 1, all the values are the same as they were in quadrant 1 before. So this thing is just going to repeat. Quadrant 2 is going to do what quadrant 2 did last time. Quadrant 3, quadrant 4. If we go back into quadrant 4 this way, it's going to do the same thing quadrant 4 did over here. So if we kind of zoomed out of this, what our sine function looks like. Oops. A little button on my pen that every once in a while I hit and it messes me up. It just looks like this wave. That goes on and on and on and on and on. And again, this is referred to as a sinusoidal wave. It might look like a light wave. It might look like a sound wave. It might look like a wave in water. And the reason it looks like all of those things is because that's what it models. We use it to model light and sound and electricity and anything that has a periodic behavior to it. Heck, even sales, sales of sweaters goes up in the winter and then down in the spring, and it's really low in the summer and then up in the fall and up in the, sales of sweaters have a sinusoidal waveform to them. We use it to model most things that oscillate nicely. That seem reasonable so far? You guys will tell me if I say something that doesn't seem reasonable. So these sinusoidal graphs have some names for some of their pieces. One oscillation, one copy of our waveform is referred to as a period. In degrees, that period naturally occurs in one rotation from 0 to 360. In radians, it occurs from 0 to 2 pi. So if somebody asked you what's the period of your sine function, well, the period of our sine function, we often use a capital T for period. I'm not actually sure why. I should look it up, try to find out why. But we often use a capital T for period. It's probably from the Latin somewhere. So in radians, our period would be 2 pi, one rotation. In degrees, it would be 360. But when we start using the sine function to model other things, we're going to want to modify that. Let's say we want to have it model tides. Well, tides oscillate over about 8 hours. So we'd want to change the period of our function so it waves over 8 hours instead of 2 pi radians. So we'll want to be able to modify that. But the natural function has a period of 2 pi, about 6 1/4. It has an amplitude. The amplitude is how much the wave deforms from the center, deforms from its equilibrium. So it's not the distance from top to bottom, it's the distance from middle to top or middle to bottom. Careful about that. And amplitude, you often think of loudness, like a stereo amplifier or a guitar amplifier. And indeed, if this was a sound wave that we were modeling, the height of that wave would indicate its loudness. How much displacement it gives in a vibration. Period, you might naturally associate with frequency. The smaller the period, the faster the wave goes, the higher the frequency. Period affects pitch in terms of sound, color in terms of light. As I mentioned, that amplitude goes from our center line, often called our equilibrium. Center line, equilibrium. And these are all things that we're going to want to be able to modify, including its start location. And I'm just going to call that's our start. We're going to have to be able to modify that. Because if we're going to use this to model things other than just a unit circle, we're going to want to be able to modify what the amplitude is, where it starts, where it stops, how long it is, where it's centered at. We want to be able to mess with all of those things and still have our nice tool. But those are the kind of the four big things we're going to be looking at whenever we try to decide what is the function that we're graphing. We're going to be looking at what is its amplitude, where does it start, how long is it, and where is it centered. Questions about that so far?
What would be a case where it would go negative? I can't think of a real world case where.
Well, got to keep in mind, negative is just a sense of measure. So if you, for example, have a swinging pendulum, right, and you call that your zero location, then one part, as it swings down from here, it was, say, 3 feet away from your equilibrium point. Well, that's 3 feet on that side. That means as it swings this way, that's negative 3 feet because it's the other direction. Fair?
That makes sense.
Okay. But that is one of the reasons we will often have a center line that moves this thing up. Like when you're talking about tides, we might want this to be, say, 4 feet up our dock. This is, say, 10 feet up our dock, and this is 16 feet up our dock. And it's going to go from 4 feet to 16 feet as it waves. So we're going to want to be able to move this around. But if you say, hey, this is where the average tide part, where the average tide level is at, then this is negative 6 feet. It's 6 feet down. Negatives are often just a direction as opposed to, a absence of, if that helps. So how are we going to modify some of these things? Probably the easiest one, well, the easiest one is usually amplitude, but since we're talking about lift here, let's talk about that one. Lift, or the technical term is vertical shift. Now, for those of you who have had Math 111 or Algebra 2, but Math 111 here, you might recall section 3.5 in Math 111, where you talked about vertical translations and horizontal translations and vertical stretches and compressions. Remember that section? And your Math 111 teacher probably said something to the effect of, be mindful of this, because for those of you going into Math 112, everything is graphed that way in Math 112.
Yep.
Well, I tell my people that. So
I've definitely heard that before.
yeah. So you can, and if you've got our copy of the textbook, you can look back at section 3.5 for a review of that if you want. But that equilibrium, that lift value is a vertical shift like it was in 3.5. So if we graph a function, or we say want a function that goes from, like I was talking about with the tides, that centers at 10 feet high, but goes up to 11 feet and down to 9 feet. So instead of going between -1 and +1, it's going between 9 and 11. It's still only going up 1 and down 1. Oops. Find a way to turn that off. So it's still the same amplitude, but we just want it to occur at a higher level. All we need to do is take our sine function and add however much we want to add for that center line. So if we have a +10 there, that center line is going to occur at 10. If we had a 7 there, it would occur at 7. If we had a -4 there, that center line would be down at -4. So, and we'd still be going up 1, down 1. So we'd still be going from -3 to -5. And that would just be y equals sine x at -4. And again, why, what might the negatives mean? We go from a loss of 3 to a loss of 5. So, as our I don't know, needs for air conditioning change over the seasons, our costs being represented by negative, goes from $3 an hour to $5 an hour, centering at about -$4 an hour over the year. This is a random example. So that vertical shift is probably the easiest one. It just takes that diagram, takes that graph and shifts it up and down, changes where our center point is. But in my example, I went, instead of going from 11 to 9, we started at 10, and then I believe we went up to 16 and down to 4. So if we want it to stretch up further and go down lower, we need to change that amplitude. We need to change how high and how low those values are going. And that's actually also a fairly nice thing to do. Anytime you're trying to affect the y values, notice our x's really aren't changing much. The x's, the width and the start position haven't changed yet. Those tend to be pretty easy to change. Changing left and right, changing the stretch and the start position, those tend to be more difficult. So if we want to change that amplitude, we just need these values, instead of going between 0 and 1, we need them to go between 0 and 3. And we can accomplish that by simply multiplying. Actually, in this case, I think it's 6, right? So yeah, from 10 to 16 would be 6. So multiply by 6, and those values are going to be 6 times the size. So instead of this being our kind of generic sine function going from 1 to -1, notice these all have the same period, 2 pi. But our y equals sine x, or generic y equals sine x, is centered at 0. It has an amplitude of 1. We can change that center by adding a constant. We can change that amplitude by multiplying with a coefficient. Let's say, for sake of argument, I wanted, let's say for sake of argument, I wanted green. I don't have a green pen up here. There we go. Let's say, for sake of argument, we wanted one that goes, this is the last one I'm going to put on this diagram. This diagram's getting kind of full. Let's say we wanted one that went negatively first. So for whatever reason, whatever we're modeling drops down before it rises up. So we've kind of want to reflect it vertically. Well, its period hasn't changed and its start position hasn't changed. So nothing's happening to that x value. The equilibrium is still at 10. So we're still going to have a plus 10. The amplitude here, if I'm going down to, say, 7, I would then be going up to, the drawing's not quite symmetric, 13. So that would be an amplitude of 3. But how am I going to make it go down first instead of up first?
Put a negative in front of the sign.
Yeah. Now that doesn't change that our amplitude is 3. Be careful about that. Our amplitude isn't -3. Amplitude is displacement from center. So our amplitude is still 3.
In the book, isn't it an absolute value?
It is, and that's how we, if we wanted to know what that amplitude was, it is the absolute value of whatever that coefficient is. So the absolute value of -3, our amplitude is just that positive value because it's supposed to represent an amount of displacement, not a direction of displacement. You know, whether your sound wave starts down or up doesn't change the loudness of the sound. So we can control where all of these things happen vertically just by modifying the coefficient in front, which we generically label A, and the constant on the end, which we generically label D. Those things being outside the function affect us up and down. But again, all of these have a period of 2 pi, have a period of about 6.28. What if we want that period to be something different? Well, what do you want that period to be? Let's hold off on specific periods for a second here, but let's say we want that period to be 1/3 of the normal period. So I want to take our y equals sine x, our y equals sine x, which goes one oscillation from 0 to 2 pi. And I want to have it happen 3 times as fast. So instead of happening, over those 6 units, I want it to happen 1 oscillation in 1/3 that length, another oscillation in 1/3 that length, and another oscillation in 1/3 that length. I want to increase the frequency 3-fold. Well, to do that, we need those x's to happen 3 times as fast. So if we want those x's to happen 3 times as fast, let's take those x's and multiply them by 3. Going to speed up our x values, speed up our oscillations by a factor of 3, and make our frequency our period 1/3 the size. So this would make our period, not pi, our period into our natural period, 2 pi, divided by this speed factor or compression factor, 3. So each of these would have a period of 2 pi over 3. What if you wanted your periods to be a lot longer? You want it to be a lot slower, lower frequency. Well, if you want it to be twice or 2 times as long, if you wanted it to be 2 times as long or twice the period, or however you want to express that, then are we going to multiply those x's by 2 to make it twice as long?
No, 0.5.
Yeah, if they're going to be twice, if it's going to be twice as long, that means our x's have to occur at half the rate. So, yeah, 1/2 x would make our period, again, always our natural period, in this case 2 pi, divided by that compression factor, which since it's a half, it's going to be stretching, but we tend to call it a compression factor. So that's going to give us a period of 4 pi. So very slow by comparison. But still, if I've drawn it correctly, going down to -1 and up to +1. Didn't change the amplitude. All we did is change the period. So if we wanted to put that all together real quick here, because I know you have to go, we'll talk more about this tomorrow. But if we want to say graph y equals 5 sine of 2x plus, I don't know, 9 for some reason. Well, we know that 9 is our lift. That's where our center line is. Your book likes to call it equilibrium. They're all fine. So that's going to happen at 9. And then with an amplitude of 5, we're going to go up 5 to 14, down 5 to 4. So our sine graph is essentially going to be caught in that little track there. And it's going to start, because we don't have a phase shift yet. We don't have a horizontal shift. We'll call them phase shifts yet. So it's going to start at 0. And its period is going to be the natural period divided by that compression factor. So pi. So it's going to go through one oscillation from 0 to pi. So one oscillation from 0 to pi. If we want to graph out to 2 pi, another oscillation from there to 2 pi. That's going to make gets back to its equilibrium halfway there. Its max at 1/4 of the way there. Its minimum at 3/4 of the way there. That seem reasonable? So just by changing those 3 values, we can control, so far, everything except where we start. Tomorrow we'll talk about how to change where we start. Questions about any of that? Okay, go play with that. Have fun with it. If something comes up, let me know. Have a wonderful day.
I have a question.
Yes, ma'am.
Can you explain what Thursday is gonna kind of look like? Because like I've never taken a test at RCC, and so I don't know like where to find the test. Do we still have class?
Yes, we'll still have class, just mostly so we can answer any questions and so forth.
Okay.
You'll notice on my calendar, there's a thing here for chapter 6 test, right?
Yes.
On your calendar, it should just say the scratch paper, right?
Yes, the chapter 6 test is grayed out.
Right. So that will ungray and occur down here. And you can click on that once the test is open. So once the test is open, it'll behave a lot like your homework assignments do. The difference is when you click on it, it will say, this is timed. Are you ready to start?
Okay. And is it open all day?
Yes.
And then you only have the hour to do it? Okay.
Yeah. And after you're done with it, you should then be sending a scan of your scratch paper to that test, that scratch paper link.
Okay.
So I can use the scratch paper to give partial credit.
Okay.
Or you
And,
want that scratch paper to be nice and neat and tidy and organized and all that kind of stuff.
Okay, sounds good. And it's not proctored, correct?
Not what?
Proctored, like we're not, somebody asked it during the class, so you're not taking it in front of somebody like with their camera on?
Yes, you're right.
Okay.
It is not proctored.
Okay. Okay, well, thank you so much.
You're very welcome.
And I appreciate you recording the lectures. They really help when I have to go back.
Oh, happy to.
Thank you. Have a good day.